modulation and shift keying techniques and all. So first we have to see the pulse modulation.
Ma'am.
Yes,
Sorry.
sir.
அம்மா அந்த மேல டிஸ்மிஸ் ஸ்கிரீன் வருது ரெக்கார்டிங்ல உங்களுக்கு அது இது பண்ண முடியுதா பாருங்க.
எனக்கு எதுமே வரலையே சார்.
சரி ஓகே ஓகே இருங்க நான் க்ளோஸ் பண்ணிக்கிறோம். ஸ்டார்ட் பண்ணுங்க. இப்போ ஸ்டார்ட் பண்ணிடுங்க. அவ்வளவுதான் ஃபர்ஸ்ட்ல இருந்து ஸ்டார்ட் பண்ணிக்கோங்க. ஸ்டார்ட்.
Okay. Good morning, one and all present here. Today we are going to start the digital communication gate classes problems. First, we are going to see the digital communication problem. We have to know the basics of digital communication. In general, this communication can be classified into two types, that is analog communication and digital communication. So in the digital communication we'll have multiple types, that is a pulse communication and shift keying techniques and all. So first of all we have to see what is mean by pulse communication. By using the pulses, that is we are going to transmit our message signal as a pulses. It's said to be a pulse communication. To transfer the pulses as a information, we have to modulate that signal. If we use a pulse signal as a message signal, then the type of modulation is said to be a pulse modulation. So what is mean by pulse modulation in the sense, a message signal, that is a pulse signal can be modulated and transmitted over the channel. That is said to be a pulse modulation. Under the pulse modulation, we have different types. So the first thing, that is the basic thing, is pulse amplitude modulation. It's simply said to be a PAM, pulse amplitude modulation signal. Next, the one of the important topic regarding this only we are going to see the problems in this session, that is pulse code modulation. So what is that PCM? That is a pulse code modulation. This is regarding, we are going to see the problem in this topic. Then the next one is DPCM, differential pulse code modulation. It is the next form of PCM. In that we are using a difference between the consecutive pulses. We'll see detail in later. Next we'll have adaptive pulse code modulation, that is ADPCM. Then we have delta modulation and DM, then adaptive delta modulation, ADM, and line coding, etc. So in this pulse modulation we have four important operations. What is the first operation is sampling and quantization. Second one is pulse modulation. Third one is we are going to use the vocoders to process that modulated signal. That vocoders is nothing but voice coders. Then it will go to your multiplexing techniques. So what is meant by multiplexing? In the sense, we are going to combine multiple signals over a single channel. That is said to be a multiplexing signal. So in that we have two different types: time division multiplexing, frequency division multiplexing, TDM and FDM. So in our topic we are going to concentrate on pulse modulation alone. For that we need a pre-processing, that is sampling and quantization. Then only we can understand about the pulse modulation. Then only we can solve the problem under this topics. Okay, so what is the thing we have to see now? Sampling and quantization. After that we are going to see a pulse modulation. In that pulse modulation, the important topic we are going to cover is pulse code modulation and differential pulse code modulation today. Next, so in basics, so what are the signals we have? It's a basic thing. In general we can divide the signals into three types, that is analog signal, a discrete signal, and digital signal. So it is the uh, it is very important that we have we have analog signal, discrete signal, and digital signal. So what is mean by analog signal? The amplitude of the analog signal is varying continuously with respect to time. What is meant by discrete signal is the amplitude of the signal is vary at the amplitude of the signal is constant in a particular time period. Okay, in digital signal we have only two amplitudes, whether it may be 1 or 0. That is half amplitude and on amplitude. Simply it is said to be like that. So what is the pulse waveform in the sense? We have two portions in that pulse waveform, that is mark and space. The width of the mark is very small compared with the space. The one cycle of the pulse waveform is calculated by adding the time period of mark and space. So compare with the space, mark duration is very less. Then a simple process we have, that is nothing but it is the simple process how the analog signal is converted into a digital data. This is the basic diagram. We don't have any other complicated elements in that. So it is a basic operation. So what is the thing we have to know that first we are going to take an analog signal for the process. The first step, we are going to take the samples of analog signal. So by using the sampler, we can take the samples. In sampling, we'll have two different types: nasal sampling, flat earth sampling, lot of that. We'll see a little bit later. So in general, we can say the analog signal is simply converted into a sampled signal. That sampled signal is said to be a pulse amplitude modulated signal. That PAM is quantized by using the quantizer, that is the amplitude of the signal, that is PAM signal, is discretized by using this process, that is the quantization process. Then the operation is said to be the quantization. Then it will go to the encoding. The quantized and discretized amplitude signal, that is quantized PAM signal, is encoded with the help of encoder. That is, that signal is converted into a digital bit, sequence of the digital bit. However, our analog signal is converted into a digital signal. Analog signal is converted into a digital signal. This operation is done by a device called ADC. What is mean by ADC in the sense? Analog to digital converter. It plays a main role. It plays a main role in digital communication and analog communication and all. Then sampling. So what is the first step involved in analog to digital conversion is sampling. Okay, here the continuous analog signal is converted into discrete digital signal. Here, by taking these samples, we can convert a continuous analog signal into a discrete digital signal. Okay. So first we are going to see what are the signals involved here, what are the frequencies, the term we have used in the problems. That is very important. All of know that what is the frequency of the signal, what is the amplitude of the signal and all. So simply I can say the notation of the message frequency is said to be FM. Message frequency is said to be FM and sample frequency is FS. We are going to take the samples by using this sample frequency alone. In sampling we'll have two different types. One of the major type is natural sampling. Another one is flat tap sampling. Why it is called a natural sampling in the sense the shape of the output waveform looks like our natural signal, that is our original signal. That's why it is said to be a natural sampling. So in this waveform you can see we have a input waveform, then the sample pulses. We are going to take this sample by using these pulses. The output signal looks like this. This is nothing but the waveform of natural sampling. Then we have two cases here. How can we take these samples? The rate of sample plays the main role. If we take the high samples, then the signal is look like this, the left side curve. If we take the if we consider the lower sample rate, the signal will look like the right side curve. So which one is the best, which one is the optimum? How can we conclude that which sampling rate is best to sample the signal? For that we have one criterion, that is said to be the Nyquist criterion. So what is that Nyquist criterion? A simple definition: a band limited signal can be fully reconstructed from its samples provided that the sampling rate exceeds twice the maximum frequency in the band limited signal. This minimum sampling rate is called the Nyquist rate. That simply we can say that is a sampling frequency can be explained or equal Fs equal 1 by Ts, or the sampling frequency should be greater than or equal to Fm. Consider this diagram. We have the input waveform. It is a sinusoidal waveform, and we have the sample pulses. Then we have the output waveform. That is the output sampled waveform. It is the natural sampled waveform. Then, if we take the high sampling rate in the sense the sampling frequency is greater than 2 times the highest frequency. That is, Fs is greater than 2Fm. Then the sampling is said to be the oversampling. Why? The signal won't be reconstructed perfectly. If we take these samples like that, we cannot reconstruct it properly. Then we'll have undersampling, that is Fs is less than 2Fm. In that we cannot reconstruct our signal properly. So what is the criterion to get, what is the criterion to get our signal is Fs should be equal to Fs should be equal to 2Fm. Fs should be equal to 2Fm. Then we can reconstruct our original signal properly. As I told already, we have undersampling, oversampling. We'll have undersampling and oversampling. We'll have undersampling and oversampling. The undersampled signal, that is low sampling rate, produces results that report false information about the analog data which does not represent the original. This phenomenon is called aliasing. One of the important thing we have to know that low sampling rate provides the aliasing, that is the over interference of the adjacent samples will create the problem is said to be the aliasing. Aliasing is one of the important drawback. How can we avoid the aliasing? Aliasing does not occur if we consider if 2f less than 1 by t, that is the sampling rate is greater than the twice the frequency of desired information, we can avoid aliasing. So it is one of the important formula. We should know that aliasing does not occur if 2f is less than, that is the sampling frequency, that is 2f is less than 2f is less than the sampling frequency, aliasing will not occur. Okay, so I repeat the once again. Aliasing does not occur if 2f less than 1 by t. 2f less than 1 by t. Look at the waveform. You can easily understand that adequately sampled signal and aliased signal due to undersampling. So this is the spectrum of oversampled signal, perfect sampling and undersampling. Types of sampling, we have three types, that is natural sampling and flat tap sampling, that is the important classification. The third one is sample and hold method. Sample and hold method. So the most problem will arise under natural sampling and flat tap sampling. Next we can see the waveform of natural sampling. As we know that the shape of the waveform looks like the natural signal. Then this is the waveform of sample and hold circuit. So we know that we'll have the analog signal here, then we'll have the control signal here. Circuit diagram of sample and hold circuit. Holding capacitor, it will charge when the analog input is on. It will charge, then once it charges, it start discharging. Then this analog output, that is this diode, will give you the output AO. During that period, we'll get the waveform like this. This is sample and hold circuit. Then we'll have flat top sampling. The sampled signal, the pulses of the sampled signal top is flat. That's why it is said to be the flat top sampling. That's why it is said to be a flat top sampling. Then next, first we have know about the sampling. So what are the things we have seen? The definition of the sampling, the types of the sampling, and the Nyquist rate, undersampling and oversampling and all. So at the Nyquist rate, if we take the samples at the Nyquist rate, we can avoid aliasing. What is meant by aliasing? Aliasing is nothing but overlapping of the adjacent frequency. This is a one kind of noise. Okay, next the important block, we are going for quantization. So what is that quantization? What is the quantizing an analog signal is said to be? The analog to digital converters perform this type of function to create a series of digital values out of the given analog signal. The figure shows that how the analog signal got into a digital, undergo the sampling and quantization. So we have the analog signal in the first block as the input. It will go to the sampling. By here we can have a flat top sampled signal. From the sampling we are getting a flat top sampled signal. By seeing the figure we can conclude that is the flat top sampled signal. Then it will go to the quantization. Now once the signal get quantized, it will go to the encoding. So what is mean by quantization? Quantization is nothing but simply representing the sampled values of the amplitude by a finite set of levels. which means a converting continuous amplitude sample into a discrete time signal. The amplitude of the continuous signal is converted into discrete. The amplitude of the continuous signal is converted into discrete is said to be a discrete time signal. If we do the samples and quantization, definitely will have some losses on the information. Okay, the quality of the quantizer output depends upon the number of quantization levels used. So what is meant by quantization levels in the sense? The quantizing of an analog signal is done by discretizing the signal with a number of quantization levels. That is said to be the quantization level. Though if the quality of the quantizer depends on the quantization levels. The discrete amplitudes of the quantized output are called as representation levels or reconstruction levels. The spacing between the two adjacent representation levels is called quantum or step size. The spacing between the two adjacent representation levels is called quantum or step size. Is one of the important parameter we should know in solving the problem. Resultant quantized signal, which is this digital form for the given analog signal, is also called as staircase waveform in accordance with its shape. The quantized signal is also said to be the staircase approximation. Like the sampling, here also we have two types in quantization. The first one is uniform quantization and non-uniform quantization. What is that uniform quantization? The step size, we know that what is mean by step size, the gap between the adjacent samples, right? So that there are two types of quantization, that is uniform quantization and non-uniform quantization. The uniform quantization is nothing but the step size is uniform, that's why it is said to be the uniform quantization. How can we say the type of quantization in which the quantization levels are uniformly spaced is termed as a uniform quantization. What is meant by non-uniform quantization? The type of quantization in which the quantization levels are unequal and mostly the relation between them is logarithmic is termed as a non-uniform quantization. Simply we can say the step size is uniform, then it is said to be the uniform quantization. If the step size is not equal, it is said to be the non-uniform quantization. In that uniform quantization, we have two types, that is nothing but mid-rise quantizer and mid-read quantizer. What is that mid-rise quantizer? In the sense, the origin of this waveform is lying in the y-axis. Okay, and it shows like a rising. That's why it is said to be the mid-rise quantizer. What is that mid-treed quantizer? In the sense, the treed portion of the staircase approximation lies in the x-axis. So it is said to be the mid-tread. Those are all the output waveform of the quantizer. So how can we conclude the output of the quantizer? And the output of the quantizer in that tread portion of the staircase approximation lies in the x-axis, then it is said to be the mid-tread quantization. The rise portion of the quantizer lies in the y-axis, then it is said to be the mid-rise quantizer. Then compounding. So in this non-uniform quantization, we have compounding operation. So how can we define as non-uniform quantizers are difficult to make and expensive. So we'll go for the compounding operation. What is mean by compounding? In the sense, the a non-linearity causes the signal amplitude to be compressed. The input to the quantizer will have a more uniform distribution. At the receiver, the signal is expanded by an inverse to the non-linearity. The process of the process of compressing and expanding is called compounding. The process of compressing and expanding is called as compounding. An alternative is to first pass the speech signal through a non-linearity before quantizing with a uniform quantizer. So look at the diagram. We'll have the input voice signal. It will go to the compressor. From the compressor, it will go to the encoder. Then it will convert it into it will transmitter over the channel. At the receiver, it will reach the decoder. Then it will go to the expander. We'll have two types of compounding, ALA and MULA compounding. These two are standard compounding methods. MULA is used in North America and Japan. ALA is used elsewhere to compress digital telephone signals. These are all the important formula, that is regarding our ALA and MULA compression. This is the MULA characteristics curve. This is ALA characteristics curve. So we have to know that ALA and MULA characteristics curve before entering into the problems. Next, one of the important thing we have to know that quantization error, the difference between the actual input and the quantized input is said to be a quantization error. We can simply define as the difference between an input value and its quantized value is called a quantization error. And the quantizer is a logarithmic function that performs quantization rounding of the value. An analog to digital converter ADC works as a quantizer. Those are the important parameter. Then we have pulse modulation. So one of the important thing we are entering into a one of the important thing, that is pulse modulation. So we have first thing, both what is the difference between square wave and pulse waveform. The simple difference in the square wave, the that is the square wave can be divided into two half, positive half and negative half. They both are having the same duration, equal duration, but in this case of pulse waveform will have two half, that is the mark and space. But in this pulse waveform the mark is very less than the space sound part. This is the major difference between square wave and pulse waveform. Pulse modulation. What is the definition for pulse modulation? In the sense, the amplitude of the pulse carrier is changed in proportion with instantaneous amplitude of the modulating signal. So simply we can say, with respect to the amplitude of message signal, the amplitude of the pulse carrier is varies. So amplitude of the message plays the main role here. With respect to the amplitude of the message signal, amplitude of the pulse carrier is varies. Amplitude of the pulse carrier is varies. It's simply said to be the pulse modulation. This is the diagrammatical representation example for pulse modulation signal. In this waveform we have in this diagram The first waveform is a message signal, sinusoidal signal. Second one is sampling signal, that is nothing but the pulse carrier. Second signal is nothing but a pulse carrier. This is pulse amplitude modulated signal. Here the amplitude of the pulses varies with respect to the amplitude of the message signal. In this PAM, we have two types: natural pulse amplitude modulation, flat top pulse amplitude modulation. So as we know that what is meant by natural PAM? Natural PAM, the output waveform, the PAM waveform, the top of the PAM waveform looks like a natural signaling. That's why it is said to be a natural PAM signal. Then we'll have the flat top PAM. The PAM that is flat top PAM. The top of the pulse, the top of the PAM signal is flat. That's why it is said to be a pulse amplitude modulated signal. Okay. Next we have natural PAM block diagram. Simply we can say we are going to feed a message signal here. This message signal will go to a low pass filter. To avoid the high frequency component, we use the low pass filter. Then it will go to the modulator. What is the another input for the modulator coming from is pulse generator, that is a carrier generator. We can say it is the carrier signal. So pulse signal considered as a carrier signal, it will go to a modulator. Then from the modulator we have pulse amplitude modulated signal. Then it will go to the pulse reshaping circuit. From the pulse reshaping circuit, we have a PAM signal. This is a simple block diagram of our PAM signal generator. How can we deduct and demodulate a PAM signal? Before deduction of PAM, we have to know what is mean by deduction or demodulation in general. In general, we can say demodulation is recovering our original message signal from the modulated signal. It is said to be the reduction or demodulation. So here pulse amplitude modulated signal, then we'll have a low pass filter, then we'll get a demodulated signal. A simple construction only. Demodulation of PAM signal. Simply we can use a low pass filter, we can get a deducted signal. Then we'll have the flat top sampling as like a natural sampling signal. Then the important formula we have to know: transmission bandwidth of PAM is, that is tau less than Ts. Then this formula we can write it as Ts less than or equal to 1 by 2 Fm. Bandwidth of the PAM signal can be defined as bandwidth is greater than Fm. Then we'll have pulse code modulation, PCM. In this pulse code modulation, simply we can say it is a digital pulse modulation technique, converts analog signal into a binary sequence. So what is the important thing we have to remember in our mind is PCM converts analog signal into a binary sequence. So what is the main elements present in the PCM is transmitter, transmission path and receiver. This is the general block diagram of our PCM system. Analog message input, it will go to a low pass filter. To avoid, low pass filter is used to avoid a high frequency component. Simply the noise signals are high frequency component. Low pass filter is used to filter the high frequency component. It allows only a low frequency component. Our message signal is simply a low frequency component. Then it will go to a sampler. By using the sampler, we are getting the sampled signal. Then it will go to the quantizer. From the quantizer, we can get the discretized amplitude signal. So the output of the quantizer is the input signal which is sampled and quantized, sampled in amplitude, quantized in time. Then it will go to the encoder. At the end of the encoder, we are getting a digital bits. The encoded bits, that bit can be transmitted over the channel by using a regenerative repeater. It simply repeats what are the input it receives without any disturbance created by the noise. At the receiver side, we'll have the regenerator, then decoder is converted our digital signal into a analog signal, then it will go to a low pass filter, then receiving end will have our information. PCM transmitter section, what is it? What is the important thing we have to know that FC is FM. The sampled frequency should be equal to FM. Then we have regenerative repeater section like this. Block diagram of PCM system, PCM receiver section. Then we'll have the differential pulse code modulation. One of the important method, that is nothing but your DPCM. A differential pulse code modulation is a signal encoder that uses the baseline of pulse code modulation but adds some functionalities based on the prediction of samples of the signal. The input can be an analog signal or a digital signal. So simply we can say this is the basics form of PCM, but we can also use prediction of the samples, not only the actual samples of the signal, we can also use prediction of the samples. Then the input signal may be analog signal as well as we can use a digital signal also. So except that prediction block or the prediction concept, DPCM is simply said to be a PCM. Okay, then these are all the PCM encoder. So we'll have the sampled input, it will go to the quantizer, it will go to the encoder. The quantized input will go as the input of prediction filter. The quantizer output will go as the input of the prediction filter to predict the next sample value of the current signal, current sample, that is the current input. This is the prediction. This prediction filter is one of the additional element we have added in PCM. Similarly, we'll have in the reduction side, we'll have a decoder. Then the output of the decoder will go as the input of the prediction filter to predict the next deducted value. Those are all the formulas for SNR's DPCM. Processing gain, that is GP is sigma m square divided sigma e square. So we'll see the problems. So one of the important thing we have to know that how can we solve the problems. Before that, simple thing I have to remember that we have seen the pulse modulation, the basics of the pulse modulation. Before going to know the pulse modulation, we have to know the sampling and quantization. So we know that what is meant by sampling, what is meant by quantization, the types of sampling, the types of quantization and all. Then we have seen the pulse modulation, the definition of the pulse modulation and the types of pulse modulation. In that we have seen only two things in the major, that is nothing but pulse code modulation and differential pulse code modulation. So what is that pulse code modulation? Here we have taken our analog signal. The pulses analog signal is modulated by using the pulse carrier, then it was converted into a coded pulses. That coded pulses is transmitted over the channel. Then it is reconstructed by using the detector. Then what is mean by DPCM, differential pulse code modulation, is it is the advanced method of PCM. Here we are using the difference of the samples to predict the next sample, to predict the samples of to predict the sample value of next samples of the input signal. Okay, so we see the problems here. One of the important thing. So the first one, which one of the following statements about differential pulse code modulation, that is DPCM, is true? Which one of the pulse code modulation, which one of the following statements about differential pulse code modulation DPCM is true? The options are: the sum of message signal sample with its prediction is quantized. The second option, the message signal sample ID directly quantized and its prediction is not used. The third option is the difference of message signal sample and a random signal is quantized. Fourth option is the difference of message signal with its prediction is quantized. The difference of message signal with its prediction is quantized. So what is the option will be the answer is the first one is the sum of message signal sample with its prediction is quantized. Look at the first thing, differential DPCM, in the sense the differential pulse code modulation. So the first option is sum of message signal sample, so obviously the first option would be come. So by using these techniques, we can identify the answers easily. So the first option we cannot say because in that word we have some. Okay. The second thing is the message signal sample directly quantized and its prediction is not used. So the second thing what you have to know that we can use only the message signal, we don't use a prediction. If it is like this, then it is said to be a PCM. In this PCM we don't use a prediction values and all. In this DPCM we are using difference between the input samples and prediction values. So the combination of these two should be the answer. Okay, so the second one won't come. Next, the difference of message signal sample and a random signal is quantized. So the first thing is satisfied, there is a difference of message signal is satisfied, but the random signal is quantized, that is false. So that the third one also won't be an answer. The fourth one, what is that fourth one? The difference of message signal with its prediction is quantized. The difference of message signal with its prediction is quantized. The fourth one will be the answer. So which one of the following statements about the differential pulse code modulation is true? Is the difference of message signal with its prediction is quantized. Then what we then we'll go for the next problem. Second one, that is a sinusoidal message signal is converted to a PCM signal using a uniform quantizer. The required signal to quantization noise ratio SQNR at the output of the quantizer is 40 dB. The minimum number of bits per sample needed to achieve the desired SQNR is. So, what is that? What is that SQNR? Signal to quantization noise ratio of PCM. If using that formula, we can find out the answer. That is nothing but 7 to 7. So simply we can use the SQNR formula, we can find out the answer. Then consider the third question. Consider binary data transmission at a rate of of 56 kbps kilobits per second using baseband binary pulse amplitude modulation. Baseband binary pulse amplitude modulation BAM, that is designed to have a raised cosine spectrum. The transmission bandwidth in kilohertz required for a roll-off factor of 0.25 is, so what will be, consider a binary data transmission. Consider a binary data transmission at a rate of 56 kbps using base band binary pulse amplitude modulation, that is designed to have a raised cosine spectrum. The transmission bandwidth required for a roll-off factor of 0.25 is 34.5 to 35.5. Then the fourth question, the modulation scheme commonly used for transmission from GSM mobile terminals is, what they are asking? Simply the modulation scheme commonly used for transmission from GSM mobile terminal is. So, which modulation technique is used in GSM mobile? That is the first option, 4 QAM, that is QAM quadrature amplitude modulation, 4 phase QAM amplitude modulation, or 16 PSK phase shift keying, or Walsh Hada Mod orthogonal codes, or Gaussian minimum shift keying technique. Which one of the modulation technique is used in GSM mobile is GMSK, that is Gaussian minimum shift keying technique. The answer is D. Then in a analog digital communication system, the overall pulse shape P of t at the receiver before the sampler as the Fourier transformation P of f, if the symbols are transmitted at the rate of 2000 symbols per second, for which of the following cases is the intersymbol interference zero? By seeing this diagram, which one is having, which waveform is having ISI is zero? We have to find out. So we have to read the question again carefully. In a digital communication system, the overall pulse shape P of t at the receiver before the sampler as the Fourier transformation P of f, if the samples are transmitted at the rate of 2000 symbols per second, for which of the following cases is the intersymbol interference zero? The third waveform having ISI is 0. The answer is the third waveform. Next question. Consider Consider a binary digital communication system which uses pulses g of t and minus g of t for transmitting bits over AWGN channel, additive wide Gaussian noise channel. If the receiver uses a matched filter, which one of the following pulses will give the minimum probability of bit error? Which one of the following pulses will give the minimum probability of bit error? The first one, the second one, the third one, and the fourth one. The option is the, and the answer is the first waveform. What is the question again? We can read. Consider a binary digital communication system which uses pulses g of t and minus G of t for transmitting bits over AWGN channel. If the receiver uses a matched filter, which one of the following pulses will give the minimum probability of bit error is the first option. Next problem we can see in a baseband communications link, frequencies up to 3500 Hz are used for signaling using a raised cosine pulse with 75% excess bandwidth and for no intersymbol interference, the maximum possible signaling rate in symbols per second is option A 1750, option B 2625, option C 4000, option D 5250. So I can read the question again. In a baseband communications link, frequencies up to 3500 Hz are used for signaling using a raised cosine pulse with 75% of excess bandwidth and for no intersymbol interference. The maximum possible signaling rate in symbols per second is 1750, option B 2625, option C 4000, option D 5250. Option C 4000 is the answer. Next problem. A binary symmetric channel, simply it's said to be BSC, binary symmetric channel, has a transition probability of 1 by 8. Transition probability of 1 by 8 if the binary transmit symbol X is such that P of X equal to 0 equal to 9 by 10, then the probability of error for an optimum receiver will be I read the question once again. A binary symmetric channel has a transition probability of 1 by 8 if the binary transmit symbol X is such that P of X equal to 0 equal to 9 by 10, then the probability of error for an optimum receiver will be option A 7 out of 80, 63 out of 80, 9 out of 10, 1 out of option D is 1 out of 10. So obviously, what is the probability of error? We are if the binary transmit symbol X is such that if P of X equal to 0, that is the true probability. The possible of receiving the correct answer P of X is 9 by 10, then what is the error probability they can ask? The error probability. So what is the remaining probability? 1 by 10. That will be the answer. Option D will be the answer. That is 1 by 10. Then an analog signal is band limited to 4 kilohertz. An analog signal is band limited to 4 kilohertz sampled at the Nyquist rate. And the samples are quantized into 4 levels, and the quantized levels are assumed to be independent and equally probable. If we transmit two quantized samples per second, the information rate is if we transmit two quantized symbols per second, the information rate is option A 1 bits per second, option B 2 bits per second, option C 3 bits per second, option D 4 bits per second. So obviously the answer will be 4 bits per second. An analog signal is band limited to 4 kilohertz, sampled at the Nyquist rate, and the samples are quantized into 4 levels. The quantized levels are assumed to be independent and equally probable. If we transmit two quantized samples per second, the information rate is 4 bits per second. Then the next question, the amplitude of random signal is the amplitude of a random signal is uniformly distributed between minus 5 volt to plus 5 volt. If the signal to quantization noise ratio required in uniformly quantizing the signal is 43.5 dB, the step size of the quantization is approximately the amplitude of the random signal is uniformly distributed between minus 5 volt to plus 5 volt. The amplitude of the input signal they are given. If the signal to quantization noise ratio required in uniformly quantizing the signal is SNR is 43.5 dB, the step size of the quantization is approximately what will be 0.0333 volt. Second option 0.05 volt. Third one is 0.0. Fourth one is 0.10 volt. The answer for the question is 0.0667 volt. That is the third one will be the answer. Then the amplitude of a random signal is uniformly distributed between minus 5 volt and plus 5 volt. If the positive values of the signals are uniformly quantized with a step size 0.05 volt and the negative values are uniformly quantized with a step size 0.1 volt, the resulting signal to quantization noise ratio is approximately 46 dB, 43.8 dB, 42, third option is 42 dB, fourth option is 40 dB. So what will be the answer is 43.8 dB. I read the question once again. The amplitude of a random signal is uniformly distributed between minus 5 volt to plus 5 volt if the positive values of the signal are uniformly quantized with a step size of 0.05 volt and the negative values are uniformly quantized with a step size of 0.1 volt. The resulting signal to quantization noise ratio is approximately option A 46 dB, option B 43.8 dB, option C 42 dB, option D 40 dB. The answer will be 43.8 dB. So at this point we can end this session. So what are the things we have covered in this session is the basics of pulse modulation, that is sampling, quantization, and the types of pulse modulation, that is pulse code modulation and differential pulse code modulation, and the problems regarding in PCM and DPCM. In the next class, we can see what are the shift keying methods available in the digital modulation scheme, that is ASK, FSK, PSK and QPSK and all. So what is that ASK, PSK, QPSK and FSK in the sense amplitude shift keying, comma, then frequency shift keying and phase shift keying. The advanced version of phase shift keying is said to be the QPSK, quadrature phase shift keying and all. So in the next session, we'll see in detail about shift keying method and regarding the problems in the shift keying, we'll see. So the one of the important thing we have to know that we have to concentrate more on the quantization topic. From that quantization, definitely we'll get a one problem in gate question. In that, the step size calculation, SNR calculation, those are all the formulas are very very important. We have to note down that problems carefully. Then in that PCM we have to know the formula about SNR calculation. And in DPCM we have to know the SNR formula to solve the problems. So we have covered some problems regarding PCM and TPCM, uniform quantization and non-uniform quantization, like that. Mm, as So we'll see the problems regarding ASK, FSK, PSK in next session. If you have are any if you have any doubts, ask me. Okay, students. Thank you for the participation. Thank you.